Let's dive right into this explainer and discover how energy acts as the ultimate connector across every single branch of science. When we study the natural world, it's really easy to put things into separate boxes. We've got biology over here, chemistry over there, physics down the hall, and earth science somewhere else entirely. But today, we're going to completely shatter those boxes, because there is one single, unified thread that weaves through absolutely everything we observe in the universe. And that thread is energy.
Think about the metaphor of a river for a second. Energy constantly changes form, from light to chemical to kinetic, but it never truly vanishes. It might be a rushing waterfall one moment, a wide, calm stream the next, or it might just evaporate right into the air. But the water itself, it hasn't ceased to exist? Well, energy behaves the exact same way. It never just appears from nothing, and it never truly disappears. It just wears different masks.
Here is our roadmap for today. First, we'll define the Great Connector. Then, we're looking at living systems, powering the atmosphere, the chemistry of bonds, the physics of motion, and finally, we'll wrap up with the energy chain.
Section 1. The Great Connector, Unifying the Sciences. Whether we're talking about biology, atmospheric science, chemistry, or mechanics, they're all governed by exactly the same rules of how energy is captured, stored, transferred, transformed, and conserved.
Section 2. Energy in living systems, from the sun to the cell. Let's start with life science, because life on Earth runs entirely on energy beamed down from the sun.
These two biological processes are essentially exact mirror images of one another. It's absolute proof that energy isn't created or destroyed, it's just transformed. In photosynthesis, the plant takes carbon dioxide, water, and pure light energy and actually packs that energy into the chemical bonds of glucose. It's literally bottling sunlight. Then you have cellular respiration. When an organism needs energy, it takes that glucose, introduces oxygen, breaks those bonds, and releases the stored energy to produce ATP and heat. It's the law of conservation of energy happening right inside your own cells.
Section 3. Powering the atmosphere, planetary energy, and weather. Now we're going to move to the macro scale and see how this same solar energy drives Earth's entire weather and climate system.
The crucial point here is that the equator gets way more energy per unit area than the poles do, and that kicks off a massive planetary chain reaction. It creates everything from a gentle breeze to a devastating hurricane. Think of it like this. The Earth is basically just trying to balance out its temperature. That intense heat at the equator causes air to rise, which changes the air pressure. High pressure moves toward low pressure, and boom, you've got wind. This unequal heating is literally the engine for our entire global climate.
But we can't talk about atmospheric energy without talking about its main fuel, which is water. Water is the ultimate atmospheric messenger here. Every single thunderstorm is actually a massive energy transfer machine. When liquid water evaporates from the ocean, it absorbs a tremendous amount of energy, what we call latent heat. That energy is carried up into the sky, secretly hidden within the water vapor. But the moment that vapor condenses to form a cloud or rain, all that hidden energy is explosively released back into the atmosphere. And that release is exactly what powers the violent updrafts of a thunderstorm.
Section 4. The chemistry of bonds, microscopic energy storage. Let's zoom all the way down from giant atmospheric storms into the microscopic world to see exactly where this energy hides.
Okay, so this is the golden rule of chemistry, and it connects to every other branch of science. Atoms bond because the bonded state is simply a lower, more comfortable energy state than being separated. Forming a bond actually releases energy, bringing the atoms into a much more stable state. Think of it like a ball rolling down into a valley. Breaking a bond, however, is like pushing that ball back up the hill. It takes work. It requires energy. So when an ionic bond forms between sodium and chlorine to make salt, the system releases energy because those bonded ions are just far more stable together than they are apart.
You can see how this microscopic bond-breaking rule perfectly explains the biology we discussed earlier, right? In photosynthesis, sunlight provides the massive energy kick required to break those stubborn bonds in water and carbon dioxide. Then, new bonds form in glucose, locking that energy into a highly accessible format. When you eat that glucose, respiration breaks it down, capturing the release to power your day. And in chemistry, the unique way metallic bonds share energy allows them to be flexible. It lets metals bend without snapping and, crucially, allows electrical currents to flow. That perfectly bridges our chemical rules straight into the realm of physics.
Section 5. Physics of motion, quantifying the flow. Speaking of physics, let's look at mechanics to see how we can put precise mathematical numbers to these energy transformations.
The law of conservation of mechanical energy proves that potential and kinetic energy simply trade places. Ke stands for kinetic energy. That's the energy of motion. Pe stands for potential energy, which is stored energy. Think of a roller coaster paused at the very top of a steep hill. Assuming there's no friction, the initial kinetic and potential energy will always equal the final kinetic and potential energy. The numbers just shuffle back and forth. As you drop down that hill, your potential energy decreases, but your kinetic energy increases by the exact same amount.
These formulas are basically your physics toolkit. They are the mechanisms and rates by which energy is transferred and quantified in the physical world. Potential energy relies on mass, gravity, and height. Kinetic energy looks at mass and velocity. But to actually transfer energy, you have to do work, which means applying force over a distance. And if you want to know how fast that energy is transferring, well, that's power. Work divided by time. It's just a beautifully complete toolkit for measuring reality.
But hold on a second. What about friction? We said the roller coaster equation only works without friction. Well, when friction enters the chat, that quote-unquote lost mechanical energy simply becomes heat. And that connects physics right back to the thermal energy of the atmosphere. Your total mechanical energy might decrease because of friction, but the grand total of energy in the universe remains exactly constant. That motion energy didn't just vanish, it turned into thermal energy, heating up the track, the wheels, and the surrounding air.
Section 6. The energy chain, tying it all together. It is time for the grand finale. We're going to synthesize all 4 branches of science into one real-world, seamless energy chain. Watch this. We are going to trace a single packet of energy from the sun right into a plant, through your digestive system, and finally down into the kinetic motion of your legs as you walk. First, Earth science. Radiant energy from a nuclear fusion reaction 93 million miles away travels through space and strikes a field of wheat. Second, life science. That wheat plant performs photosynthesis, capturing the light and forging it into the chemical bonds of glucose. Third, chemistry. You eat a slice of bread made from that wheat. Your body's chemical processes break apart those glucose bonds, releasing the stored energy to forge ATP. And finally, physics. That ATP provides the localized energy for your muscle fibers to contract, turning chemical potential energy into mechanical kinetic energy as you walk down the street.
And here is the truly brilliant part. Because of friction, the heat generated by your shoes rubbing against the pavement warms the surrounding air, looping our chain entirely back to Earth science. The kinetic energy of your walking is transformed into thermal energy. You are slightly, incrementally warming the atmosphere around you. You are literally contributing to the very thermal energy that drives the weather systems we talked about earlier. The loop is totally closed. It is one continuous, unbroken river of energy.
As we wrap up this explainer, I really want you to think deeper about this. Try to trace the flow of energy in your next action. Because once you see the energy river, you see how all of science connects. Whether you're turning the key in your car, boiling water for tea, or honestly just taking a deep breath, you are an active participant in this incredible cosmic relay race. Energy is the great connector. So I leave you with this. What is the energy chain of the very next thing you do today? Trace it back. I promise you, it's going to completely change the way you see the world.